Now, typically when you're preparing to do a study, you need to know how big your sample size is going to be before you get too far into it. You don't want to do your study, get your calculations, and then find out that you didn't have enough people to do your survey, or you didn't weigh enough, whatever it is you were going to weigh, house cats or what have you, in order to have your confidence interval have a certain or margin of error. So you want to plan this sort of a thing in advance. Sometimes the information we use in these are based on sort of previous small studies to get estimates, and then we scale up. But sometimes we have things that we think are true, and we use those in our estimates. Now, if we're calculating the sample size for a means problem or calculating the sample size for a proportion problem, we have two slightly different formulas. Both of these formulas are basically the margin of error formulas that we had before when we were calculating confidence intervals. And then we're rearranging that formula in order to solve for n, the sample size. And so because that's the procedure that we used, I've left these formulas as n, but when we get values, n has to be an integer. And so what we want to really think of these as is sort of thresholds. The n that we really end up with in the end, we should always think of this being, this is a minimum value to get what we're looking for. And we should never round down. We should always round up to the next whole value. If I say that I need 4.1 observations, 4 is not going to cut it. I need to go up to 4 plus 1, so 5. I need to go to 5. Even though it's 0.1, I need to go up to 5. So think about it as that is a threshold. Now, both of these formulas are going to use z-scores in them. Means problems, we typically calculate margins of error using t-scores, but t-scores depend on the degrees of freedom, and that's the sample size. So we can't actually use t-scores here. So we are going to get an estimate essentially from using the normal distribution, the standard normal distribution. But then if your sample size is particularly small, normally you want to round up because if for no other reason than because your z-score is an estimate. And when you actually calculate your margin of error, it will be wider than it would be if you were using the normal distribution. So for all kinds of reasons, always round up to the next whole number, never down. Now, let's take these formulas, let's go to Excel and actually do some calculations. Now, for most of the time, you're going to use 95% as your standard confidence interval, which is 1.96. As we've done in previous videos, to get your 1.96, you want to calculate your probability to be the right tail, so you get a positive value. 1 minus a 95% confidence interval leaves 5% in the tail. That's your alpha. 0.05 divided by 2, so 2.5% in each tail. You can let Excel do this math for you. The mean, again, this is a standard score, so we put in 0 and 1. That's our 1.96. Now, let's say we're trying to get a better estimate of our weight of house cats that we had in a previous video. The standard deviation we got from that sample was estimated to be 2.3. And let's say instead of having our confidence interval be about 4 pounds wide, basically, 2 on either end, let's say we wanted to shrink our margin of error down to 1 pound in either direction. Then we're going to use our sample size formula. N is going to be the square of Z times the standard error, the standard deviation divided by the margin of error, all of that squared. Now, if you think it's easier for you not to work with the parentheses, but to square everything individually, that's fine. But the square in the parentheses is to square everything. Now, again, what does this mean? This means that the minimum value that we need is 20.3 to get this margin of error. And so we really want to get this margin of error to be 1 pound, not 1 pound and a little bit, but literally 1 pound or less. Then the sample size we need is 21. It is to round up, regardless of what this decimal place is. Now, we can do the same kind of thing for a proportion problem. Now, the difficulty with a proportion problem is that they don't always tell you the sample proportion that you're working with. If they do, that's great, you can use it. So if we think back to a previous video where we were calculating a confidence interval around 35% for our bank stability question, what if we wanted to get that margin of error not to be 4.5%, but we wanted it to be lower for the 95% confidence level? This is our 1.96 again. Then what we want to be able to do is, actually, you can use 1.96. It's very, very close. If you don't want to recalculate it, but it's important to know how to calculate it in case the confidence level you're looking for is not 95%, maybe it's 99%, then you need to recalculate. Sorry. Z-score goes there. The proportion value in that particular bank stability problem was 35%. And if you're going to go with that as sort of your sample, then that's great. You can use that. The margin of error, let's say we want to get this down to, let's say, 3%. Now, you need to be careful with this. 3% is not a 3. It's 3%. It's important to keep that in mind. You either have to write these as decimals or as percent with the percent sign, percentages with the percent sign. Excel will be able to go from there, but you can't use 35 and 3. Now, the formula for the proportion is a little different. It's P times 1 minus P. And then the Z is squared, because remember, P and 1 minus P in the margin of error formula are already under the square root. So they are not re-squared in order to cancel the square root around N. We just canceled the square root around these two. But then the Z has to be squared. And the margin of error has to be squared. This is very important. You will not get a good answer if you do not square both of these. As I said, the sample sizes for proportion problems tend to be very large. We have to round up. It does not matter how small this decimal place is. You have to round up to 972. Now, as I said, there are sometimes difficulties in proportion problems where they don't specify what the proportion is that they're working from. In those cases, you would have to use the default value of 0.5. 0.5 is where the confidence interval or the margin of error are going to be the largest, and therefore oops, that's my fault. That's where the confidence interval or where the margin of error is going to be the largest. And so if you're not sure what the true population proportion is, even in a ballpark, you just assume the worst. You assume it's at the widest point possible. And then you will guarantee then that you you get enough people in your sample to ensure that regardless of where the proportion is, it will always, the confidence interval, the margin of error will always be smaller than what you need it to be. And so in this case, if you need it to be 3%, again, notice the proportion at 50%, it's gone up to 168 or 1068. Again, even though this is a very small decimal, always round up. Now, if I were to put in a different proportion, it will go down again. So regardless of if I put in a proportion that's higher than 0.5, it'll go back down again because the formula has the P times 1 minus P. So if I put in 0.35 here, that's 0.35 and 0.65. But if I put in 0.65 here, that's 0.65 and 0.35, and it's the same thing. So all of these are going to be smaller than when you have it at 0.5. So if the problem doesn't specify, you assume 0.5 as the worst case scenario and you calculate from there. But it can be tricky because it seems like you're missing information, but you're not. You're using this default value. Telling these apart, the easiest way to tell these apart is you need a standard deviation for the means question. If you have no standard deviation, it's asking about a proportion.